Swayam Prabha. Digital India. Educated India.
What's the idea of a cutting plane method? The idea of the cutting plane method is, suppose you have an optimization problem in which you have a feasible region that looks like this sort of a convex set. What it would do is it would try to approximate this convex feasible region using hyperplanes. It would try to approximate this convex feasible region using a hyperplanes, and at each iteration try to improve the description or the description of these hyperplanes. In other words, it will keep adding hyperplanes to this feasible region to the point where the approximation starts getting to the point where it starts looking almost like the original constraint. Now, the beauty is, because you are adding hyperplanes at each step, what you are minimizing over at each step is not the original convex problem, convex region, but rather just a polyhedron. Now, if so, this sort of a problem is potentially much easier, because you can use techniques that are available for linear programming in order to address this particular problem. Now, you would obviously ask, how would you use linear programming here, because your objective is not necessarily linear, but then there is a very simple trick to actually convert any optimization problem to a problem where the objective is linear. All right. So, let me first tell you this. So, suppose if I have an optimization problem like this, where you are minimizing f x subject to x in S. Is there a way by which I can convert this problem to a problem where the variable now is x? Is there a way by which I can convert this problem to a problem where the objective is linear? So, the answer to this is yes, you can do this. You can introduce a new variable t and do a minimization over x as well as t, and add an additional constraint which says simply that f of x is less than equal to t, in addition to x lying in S. Now, any of you can check that this problem is these problems are actually equivalent. Minimizing this over t and x is the same as minimizing just simply f x over x, right. So, what has happened as a result? As a result, your objective function, which could have been any nonlinear objective function here, has now become, the objective has now become linear. Which is, so this is one of the reasons why it's actually somehow in optimization, people tend to think that the difficulty in optimization is always to do with the objective, whereas in reality the difficulty is all in the constraints. Or any kind of complication in the objective can always be pushed into the constraints. So, the geometry of the constraints is what makes the problem hard, not so much the geometry of the objective. So, without loss of generality, any optimization problem can be written as an optimization of a linear function over some constraints, and that is what we have done here. So, as a result of this, what we can do is we can start off assuming that this here is the form in which we have been given a problem. We have been given a problem in which we are minimizing some linear function. So, let us say you are minimizing some linear function C transpose x subject to convex constraints g I of x less than equal to 0. There are, say, m convex constraints, I going from 1 to m, all right. Now, the cutting plane method, which is what I am talking about here. So, let us write that here, cutting plane method. So, what a cutting plane method would do is, is this. So, in an abstract form, what the general form is, so it would given a polyhedron, you at each iteration k, you have a polyhedron p k. So, so we are going to assume that the objective, assume that you are minimizing C transpose x subject to x in S at, okay, at each iteration k. This is your original problem. At each iteration k, you have a polyhedron p k that outer approximates S. We have a polyhedron p k that outer approximates S. Right. Now, what you do is, instead of solving the original problem, you do this, you minimize C transpose x subject to x in now in p k. Now, this here is a linear program. This is now a linear program, all right. So, if x k belongs to S, that means if it is feasible for the original problem, one can stop, because you have now found a solution of a lesser constraint problem that is feasible also for your original problem. So, you can now you can stop and declare this as the solution, all right. But if x k is not feasible for the original problem, then what do we do? Well, if x k is not feasible for the original problem, then you are in this situation where you have found, say, a point like this. Say, suppose this is your original feasible region here, and you have constructed an approximation of it using these using hyperplanes and got to p k, and you have now found an optimal solution, say, at this corner point here, and this is suppose your x k at this stage. Now, what is this x k is not in the feasible region S, but the feasible region S is convex and x k is outside it. Then what that tells us is that there must therefore exist another hyperplane like this. There must exist a separating hyperplane, a hyperplane that separates x k from S, right. And what one can do then is that, well, add this hyperplane to your definition of p k. Okay. So, effectively and that would then tighten the original hyperplane p k and generate for you a new the original polyhedron p k and generate for you a new polyhedron p k plus 1, right. And then you are minimize then C transpose x over p k plus 1 and then go on, right. So, if x k is not in S, what one does is find a hyperplane separating x k and S, okay, and then define p k, say, denoted by say A transpose x less than equal A k transpose x less than equal to B k. Okay. So, suppose this is your hyperplane. So, then you just simply define p k plus 1 as p k intersection x such that A transpose x, A k transpose x k less than equal to B k. So, what has happened is your original hyperplane, the original set was this pk as that has been outlined. Now, the new set, the new constraints would be this, 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 and so on. And with each iteration, your outer polyhedron will continue to shrink, and it will continue to better approximate the feasible region. And so, the advantage of this is that at every step you are only solving a linear program, and if solving that linear program is cheap and is something that you can do easily, you can effectively solve a convex optimization problem using linear programming. All right. So, now why do we need this to be convex? Because we need the guarantee that a separating hyperplane exists. So, that is something that we have only in the case of a convex optimization problem. The other reason why this convex optimization works very neatly with this is because the generation of these new hyperplanes, okay, defining these new hyperplanes becomes very easy when the problem is convex. So, for example, in this particular problem that I wrote out here, where your constraints are gi of x less than equal to 0 for I from 1 to m. So, if your point is infeasible, so if your xk if xk is greater than 0, sorry, if xk is infeasible, which is effectively saying that gi of xk is greater than 0, okay, then what one does is, what one can do is simply notice the following. So, notice that so these are, I assume that these are all convex. Okay. So, if xk is infeasible, that is gi of xk is greater than 0, and for let us suppose you choose the I which is most infeasible, that means gi of xk is also greater than equal to gj of xk for all j going from 1 to m. Okay. All right. So, if this is the most infeasible one out of these, right. So, then you can, then in that case the new cutting plane or the new hyperplane, separating hyperplane is defined as x such that gi of xk plus gradient of gi of xk transpose x minus xk is less than equal to 0. All right. Now, this is a hyperplane in x, and it is defined in terms of xk. So, this is linear in x, and xk is simply a parameter here. Now, why is this a separating hyperplane? The reason for that is, well, because if I take any point that is feasible, so for any feasible point, any feasible y, it must be that gi of y is less than equal to 0, and from convexity it also has to be that this is greater than equal to gi of, by convexity this has to also be greater than equal to gi of xk plus gradient of gi of xk transpose y minus xk, right. So, what does this mean? That any feasible y will always satisfy this particular thing. That means, in particular this equation here, this here should be less than equal to 0, right, whereas on the other, yeah. So, this particular thing would always be less than equal to 0. So, what does this mean? So, this means that all feasible the entire feasible region of your problem, okay, the entire feasible region of your problem must be contained in this particular half space, this half space that is written, that is defined here, right. So, when you find a point xk, you just add this particular inequality constraint to your definition of your polyhedron pk, and that gives you an additional half space in that contains, okay, that defines for you this half space here that contains the original feasible region, right. So, so in short, by this is what the summary is, that if you have a convex optimization problem like this, this particular this simple tangent condition of convexity also gives us ways of generating hyperplanes that would of the kind that we require, right. Okay. So, with this I think I can I will wind up this lecture, and we will take up interior point methods in the next lecture.